Good to go. So, okay, so a couple of announcements first, right? So I accidentally forgot to assign a quiz, but I forgot to assign it on Friday. And so I assigned it yesterday. So please do the quiz, and it's due on Thursday. Then we accidentally released the solution to the original homework too. We just left it online, which is good and bad. So I think, I get very excited about redoing homework too slightly, or like advancing it a little bit forward, because I think it's a very valuable skill. So the part which we released, you can just look over and learn how to do it, right? And then the second part, which will really ask you to relocate a symbol or a couple of symbols, right? It's really what we were discussing here in class, and kind of getting to that level will help you. Like that's kind of like I think it got only better. But again, so I haven't released it yet because we were working on it for over the weekend, but got slow a little. But so we'll finish today, hopefully in a couple of hours, and it gets assigned.
So part 2 will be updated, right?
Right. So in part 1 will be kind of a tutorial which you read over, understand what's going on, like look through the source code, and then you're done, right? And part 2 will ask you to actually build something. And there will be a question about, again, I try to force everyone to learn how to use GDB, right? Because that's the tool which you have to be able to use in order to solve like some more like harder corner cases, which will show up later. So there will be a question about GDB as well, like explain something, explain a crash essentially, which like if you don't relocate the symbols in that L file which you're loading, it will crash and you'll have to explain why. Okay, good. So this is where we are. And just to remind where we were and what is that we're doing. So this is the lecture, right? So remember what we've done. We understood what's inside the process, spent a fair amount of time. We're about to start booting into the operating system kernel. And to do that, we need to set up those mechanisms on the CPU, which implement address translation, right? On x86 machines, there are two mechanisms, segmentation and paging, right? Those mechanisms will provide an abstraction of a virtualized memory, meaning that each process will have its own address 0, right? And somehow, if you issue a load instruction to address 0, it will go somewhere in physical memory, and it will be different from other processes, right? And we'll understand how to do that. And so we started a little bit we just started talking about it. So the idea here is that from our intro lecture, we know that we want to get to the point when we're running multiple programs, right? And the operating system will switch between them. And, there are multiple ways to do that, right? And I ask you a question like, if you have one physical memory, like here, for example, how will you share it between these two programs, the green and blue one? And at some point you suggested, okay, we can actually swap it to disk. So every time you about to start running a blue one, you just copy everything to disk temporarily, load the green one from disk and run, right? But it's obviously inefficient. And what we agreed on is that, by the way, we can probably make sure that we can fit both of these in a single physical memory, right? If it's like a address 0 and this is address max, and the green one runs here and the blue one runs here, and our knowledge about what's inside those binaries, like the text, code, data section, right, stack, allow us to do this, right? So we say, look, if we can just relocate them differently, they will never overlap in memory and they will run happily, right? Right, and that's the idea which I was introducing last time. So technically, you can build it in software, right? So you say, look, by the way, if you relocate the green one here to run at address 0 and the yellow one to run at address 1 and 4 zeros, right? So they will be sitting, and like literally one will be sitting here, another will be sitting here, and they will never overlap. And you can make sure that the text section of blue one will be here, the data section will be here, heap growing this way and a stack growing this way, right? And then I ask a question, okay, this is perfect, will work for something like Adreno, maybe even Roomba, maybe for some embedded system, but there is a real problem here. So who can tell me what this problem was? Just to wake up. But we will do a poll in a second just to wake up. Why would we fall asleep? So what's the problem? Oh, that person.
It's a security problem or one process.
Correct. Ah, man, this homework, forget, like, yeah, hold on, sorry. You remind me of something. Okay, you're absolutely right. What you're saying is that a security problem, which allows this green program to issue an address saying, okay, I want to move something, for example, from address which is contained in EAX into my EBX, right? Intel syntax, right? And this EAX might be pointing somewhere over here, right? In the address space of the yellow program, right? So which allows you to read a secret, which is kept here on a heap of the yellow program, right? And what I just got reminded of that after the lecture last time, someone came and asked me, okay, but how will it happen? Like, why would the green one read the memory of a yellow one? And my plan over the weekend was actually to come up with an example, and I promise I will do that later, just an example of a simple exploit for how it can happen. But can someone tell me how this actually can happen? So assume this is a like reasonably good C program, right? How come we can get to a state where EAX is pointing to somewhere in this yellow region instead of the green region? Who can tell me? Buffer overflow. So what is a buffer overflow? Can you explain for everyone who? Correct. So I just wanted to briefly explain how those mistakes can happen in a C program. So in a program like C, imagine this is, I'll draw our stack. And imagine you allocated some array on a stack, like a buffer. And imagine above this array, there will be an EBP pointer. And what will be here above EBP? The stack grows this way. Who can tell me what sits here? Return address, right? So this is a return address. Imagine you have some kind of a code which reads this buffer as an input. Maybe even it's a user input, like you say, like enter your name. And maybe you allocated big enough buffer. Maybe it's 256 bytes because you believe there are no names longer than 256 bytes, right? But maybe the user is so bad that they decide, well, I will enter 256 bytes plus another 8 bytes, right, into this input. So if you do something like, maybe it's a loop which reads everything character by character, and the loop is, or maybe it's like some kind of a function like scan, which scans the entire string until it reaches the zero termination sign, right? So what happens if you enter a slightly longer string which is read into this buffer? I don't remember the syntax for scan, right? So what will happen? So your name will be here. It will start with A-N-T-O-N for me. And then I will put some characters until I reach like past the length of the buffer. And I will start essentially overriding space allocated above the buffer on a stack. And I can, for example, I'll like override the return address, right? Is that clear to you? That if I enter more characters, the scan function will happily like go past the buffer if I don't enforce the check on the length of the buffer, right? This 256 bytes. And then what happens if I override the return address? Right, so I can jump anywhere in a program. And eventually, depending on where I jump, like I can jump to, for example, a move instruction, which does something like this. And depending on the value of EAX, I can access the address which is there, which is in the EAX, right? And at this point, I control what is going on in a program, right? So I can theoretically, not theoretically, in practice, I can construct, in most cases, I can construct the Turing complete computation by just jumping between different like parts of the program which have this ret instructions, right? So it's called return-oriented programming, right? So which is a powerful way of like subvert control flow without really like executing anything what is already allowed for execution. Okay, maybe that's a little bit too fast to explain how it works, but you got the point. So, right. So for example, if I'm clever enough and maybe this EAX is pushed or popped from a stack somewhere, like I find a gadget, like I find a sequence of instruction which pops EAX from the stack, right? That's my logical target. Then I say, look, by the way, if I want to control the value of EAX, I will just simply put it here by saying, okay, whatever the address I like, maybe this is the address A, I put it here on a stack, right, with my name, right? Because when I was putting my name, I will just encode the same bytes. And then I will jump exactly here. Like I first pop this value from the stack into EAX, and then my move instruction will read something like that, right? So again, maybe it's a very short introduction to how to exploit stuff, and we should spend a little bit more time with good examples. I'm glad that some people know. Let me ask, so how many people were taking a class which was teaching those things? And what is this class? Cool. And so how many people never seen anything like that? So, okay, so then everyone knows, right? So everyone knows how exploits work, and maybe I don't have to like spend a lot of time. Cool. So then we understand, okay, so we need to make sure that no matter what, even if I do my trick with scanf, and like in practice, every C program will contain a bug like this, just because it's almost humanly impossible to write a correct program. Then we need to make sure that I cannot issue instructions with EAX values, which are past my allowed range, right? Okay, so, and last time I was saying, okay, cool. Like isolation is a problem. So, and I asked you a question like, how can we solve it? And I hinted that it can be solved in software. So, and I actually wanna hear your thoughts. So I have a poll for this. No, actually, let's first discuss. Let's discuss a little bit, because maybe it's too much to do a poll right away. So what do you think? What can we do to prevent this behavior in software, purely in software, no hardware support?
Check the some
Have the kernel check that the address is valid before.
within the process.
Let's be a little bit more concrete. Again, let's imagine we have this move instruction with my EAX value here, which loads something into EBX. What kind of check do you suggest in front of this instruction? I agree with you that conceptually, yes, we need to perform a check. The question is how. How can we do it? Okay.
So every program should have some address range. So here we can check whether the EX is within the range. If it's out of the range, it's invalid.
Correct. And so how would you physically perform this check? So what's your solution to that? Imagine, even for the sake of it, you may dedicate a special register. Like instead of maintaining a frame pointer, EBP will contain the upper range.
Yeah.
For each process, it will contain the upper address. And if you care about the lower address, you will, let's take another register, let's say ESX or something, whatever we want to have. SI, right? So then what? You have the lower and the upper range in two registers. Then what do you do next?
Just verify that a memory lookups address is within.
Okay, yeah, I agree. So maybe I'm not entirely clear about like what is it I'm asking, but like which part of the system will do this check? How do you want to do it? Like again, we agreed that we're not going to ask for additional hardware support, so we cannot change the CPU, right? So we need to change the software. So what part of the software are we going to change to do this check? Well, you wanna do like a call into a kernel here, like a syscall. Correct. No, hold on. Like your idea about a syscall is actually not the most absurd one, because you say, look, like and imagine, I never explained how to invoke a syscall, but imagine you can just invoke a syscall with a simple int, and this is really true, instruction which passes a special interrupt number. And at this point, kernel gets control. And the kernel can check the value of EAX register, right? And kernel, though, has to like take a look at the value of the next instruction after this int, understand that it's a move instruction, right? Understand the semantics of it, understand that it tries to load from EAX and check the value of EAX, right? Doable, that's a solution, but what's wrong with this? Too slow, right? And because syscall, you have to decode instructions, stuff like that. So how can you improve? No, like you kind of like, you started on that. You said, look, I need some kind of language support. So instead of like using the syscall mechanism, I can just do something. You say language support, but really like it's orthogonal to a language. So you can take a binary and say, look, in that binary, in front of every move instruction, I will just simply inject this check. Like imagine I have like some kind of a compiler pass. If you have a source code, then it, of course, not orthogonal to a language. So you are with the language, but or even you can just take a binary and say, look, I will do a rewrite pass on a binary, right? So you find all move instructions in the binary and say in front of them, I will insert a check, like a sequence of instructions, like comparisons, which essentially checks that EAX value is in range, right? And this is roughly how it's done, right? So in practice, those checks are slightly optimized, and instead of like doing two registers, the encoding is the following. So you have a register, let's say something, EBP, for example, which contains the base, and you say you limit the length of the segment. For example, you can say 16 megabytes, or you can say 1 gigabyte. And then you mask essentially everything. So essentially you do a mask saying that I for sure know that the top bits of the address are zeros, and whatever is here will be within this range. And then EBP contains the number of the segment, and you essentially just copy like 1, 2, or 3 into this upper bits, like letting effectively program to access just this segment, right? Like, is this idea clear that it can be done like that? And this is how this two modern solutions, so the one which became a de facto standard, which is called WASM, right, WebAssembly, works. And before WASM, the solution which, in general, this approach is called software fault isolation. It was invented maybe like 30 years ago. And then the most recent practical solution before WASM, which comes up with this fast encoding of this check, was Google Knuckle, right? And that was the first time when we were running Quake in a browser roughly 10, 15 years ago, where Google said, okay, you take a Quake engine written in C++, we do a binary pass, we make sure that all these move instructions and other instructions which access memory are within the range, sometimes this binary pass fails because disassembly is not always decidable, because you can construct the machine code which cannot be disassembled correctly. But if it's coming out of a legit compiler, in most cases, it's possible. And so here you go, Quake runs in the browser on top of a tiny operating system which implements open, close, and other system calls which Quake needs inside the browser, translating them into like whatever engine you're using, Mozilla Firefox or Google Chrome, right? So that's pretty cool. Question? Correct, right. And you can, the question is legit. So you're asking at what time you can do it. So typically it was done like WebAssembly, you typically compile offline, right? So, although you can say like, it doesn't matter, I can do it like at the time of loading the program. And that moves us towards something what is a slightly different approach, but like similar in spirit, which is called just-in-time compiling. So JIT compilers can, or like there's a spectrum, like you compile statically, you compile when you see every new instruction as you execute it, which is a JIT. And in the middle, you can say, I can do it at the time of loading, and I can recompile everything. Typically for WebAssembly and Knuckle, it's done at the time of like statically, even before loading, right? Okay, cool. So this is the powerful observation that you can do it in software. And surprisingly, this trick can be actually reasonably fast. So how can we reason about the performance of this? If I ask you, okay, what overhead do you think WASM can introduce in your, this rewriting can introduce in your program? Again, Google level interview. I don't know when I say Google. Maybe Google is no longer popular. Whatever is your company, dream company. So what's the overhead? How can you go about it? Any guesses? Wildly slow, okay-ish, percentage-wise? No, you need to have some line of reasoning to tell me, okay, it will be X times slower, or 5% slower, or something. Agree. Compiling will take longer. That's why it's typically done once, and then the binary is there. Correct. Yeah, both of those arguments are correct. But still, like, what would be the overhead? Can you guess? Just give me a number. No, like it's a good skill to guess performance, right? Because no. Overhead of this instrumentation. Like, imagine you take a like regular Quake binary, and you said, okay, I will instrument it with those checks in front of every move instruction and some other checks which I didn't cover. How much slower my Quake will be? 10%? Why 10?
Let's think of that. The register access and memory access.
Correct. But okay, so to go about it, you need to come up with the kind of a frequency of move instructions in your code, right? So how frequent move instructions in a typical, what? Very, but what is every how many instructions? Typically every fifth instructions, yeah. Every fifth instruction is a load or store, right? And so roughly you can say, look, if I add some checks in front of every fifth instruction, so it will penalize me. Roughly you can say, look, maybe it's like 20%, just out of the blue, right? But it's at least some line of reasoning, right? And in practice, the overhead varies, right? So sometimes it's like 5%, and sometimes it goes to 100%. depending on the frequencies of loads and stores dependencies between them and stuff like that, right? So there is a fair amount of work which studies it. And this these overheads are overheads of WASM as well, because WASM is becoming vastly popular these days. You're deploying solutions on the edge, meaning that somewhere in the cloud, you can deploy your binary, which does something on the network stream, for example. And the isolation will be this, just because it's a fast way of deploying something. But those will be the overheads. And that's pretty cool. So if I ask you another question, I only talked about the check in front of a move instruction. So, and this is where we get to this, for example, this is a very simple example, right? So it has a main function which has two local variables A and B and computes the sum of A and B. This is what it's compiled into. Where in this binary we have to inject those checks. And just to make it a wake up, let's do a poll and read the suggestions. Enable it. Which lines or which addresses have to be patched to make sure that we actually are made it live. Actually, it's an open-ended question. It's hard even for me, to be honest. But let's listen to some answers, and then we'll go and come up with some understanding, again, maybe partial. This is what where's my poll everywhere? This is what we have on poll everywhere. Checks before 6D, 14, and 17. And okay, yeah, we can't even 6D. The question is, okay, so how do we do that on Mac? Like this, split? Oh, no, this. No, not like this. So how do we split a window on Mac? Do you guys remember? This. Really, to choose poll everywhere. All right, let's see. Okay, so 14, 17. So, man, what's going on? Checks before 6D, 14, and 17. 6D, 14, 17. Checks before two move instructions. Put checks before the move instruction. Some people say operating system level isolation. Check addresses of memory. Okay, that's a little off. Okay, let's go ahead and see what's going on there. So again, just for the sec, let's just concentrate. So everyone kind of guesses that we need to do a check. We need to do a check in front of every move instruction, right? So if frequency of moves here is higher, and that's because we didn't do any optimizations, right? So it's optimization level or no optimizations at all, right? So that's why we have higher level, like amounts of higher frequency of move instructions. Correct, I agree. So, however, like these 4 move instructions that obviously require a check. Let's talk about this one. Does this one require a check? No, right? But what if you already subverted the control flow, like did this buffer override or overflow, and you're somehow looping, pushing more and more stuff on the stack? At what point your stack will actually spill into the address space of other program? You believe that it's possible because push touches the stack, right?
Yeah.
So which means that probably we do need a check in front of a push to check that the ESP is in range, right? And we know that it will go one way, so the check might be a little bit simpler, but you need to check that you have at least 4 bytes before the end of your segment. Agree with this?
Yes.
A little unusual, right? That's fine. So this separation is on register, so probably one don't have to do anything. What about this one? Involve CSP. Correct. So if I understand correctly what you're saying, okay, forget about this one. It can modify ESP to anything, but we will catch it later when we will do the push, right? I agree with that. Okay, that's a meaningful approach. This we're gonna leave alone. Remember, leaf pops it pops into the EBP, right, and adjust the ESP. So here we also will need to do a check to make sure that that ESP is pointing somewhere in the legit segment, right? What about this red instruction? This is an interesting one.
Jump to return address.
Right, so jumps to return address. So is it dangerous or not?
Yes, whether the return address is the actual return address.
Correct, because look, like remember, my buffer overflow was allowing me to overwrite return address on the stack, right?
Yeah.
Which means probably in front of this return, we should inspect what is there on a stack and where is that we're jumping, right? Agree with this?
Yes.
But here's the most like interesting bit of this comes, like we got it. So we want to jump back into the segment, right? So we can check that whatever the value is there on a stack is within the range between the start and an end of the address. But is it sufficient or not? By my voice, you can guess that it's not sufficient.
No.
But why? Do you know? No. That's one good logic. Maybe I can jump on a stack and say I'll start executing something what sits there on a stack, which we never instrumented, right? Or in a heap, for example. That's a good point. So we have to protect against it, right? So you got the point. So what your classmate, actually, I missed that. What you're saying is that, like, if you have an attack and you injected something on a stack, which is executable code, if you jump on a stack, you can start executing those moves instructions, right? And we never did any checks because we thought it's a stack, right? So clearly a problem. So typically, you have 2 options of doing that. So you have to make sure that stack is not executable. If you don't have any hardware support, the stack has to live outside of your executable segments, or those checks should account for that. So when you essentially do this, like returns, you need to make sure that you're not returning on the heap or on the stack, right? And you also have to make sure that the code section is read-only somehow, right? So again, either through the checks to make sure that moves do not change the code section of a program, because they will invalidate your checks, right? Agree with this? So it's a little tricky. Then you had another suggestion.
Doesn't the stack alter your own text?
Correct. Yeah. So this, like, yeah, you have to Like you have to somehow make sure that those problems are solved, right? So you have to protect against it. Yeah. And you're right. So it quickly gets a little bit more complicated than just checks in front of moves, but still I argue manageable. And the bit which I wanted to like emphasize is that what if you're returning somewhere here? Like it's literally in the middle of a move instruction. Like clearly, well, I don't really know, but I'm guessing that 05 is a valid x86 opcode. There is a table, we can look it up. And the CPU will happily interpret this as some kind of instruction. If you're clever enough, which means that you already bypassed the check, right? So because, and maybe it's another move happens to be, right? That's bad. So at this point, you have to make sure that either you return to specific like alignment, like essentially beginning of an instruction block, and you can never return in the middle, meaning that if you can return anywhere, but the checks, all the checks and the instructions will be within the block, and the block can be like, let's say 16 bytes, for example. Or you can like do a stricter policy saying that really there is my compiler generated something what is called a control flow, and you can only return to a specific parts in a program where this function is allowed to return, because the compiler knew that it was called from A and B, and so you can return only inside A and B. And then you can look up in a table saying, okay, am I returning to one of these allowed values? You say yes, then you return. If not, it's an exception. Okay, so that's how it works, right? And that's what I wanted to illustrate, that this is essentially one way to do it. And again, the reason I'm doing it, because LASM is a very popular technology. Like I see students who want to do research on BASM. So essentially, BASM is this essentially how to enforce isolation in software, plus some other things, right? But that's a lot of fun. Let me quickly disable the poll. I appreciate your responses. Where is it? And we will move forward. However, okay, so let me, okay, I wanted to show maybe a table with overheads, but maybe forget about it. Maybe it's not as important. Here's my, keep this one. Okay, so we got it. So, but obviously with all this complexity, which we kind of just analyzed, we say, okay, but maybe let's just ask hardware to provide those checks for us, right? So imagine you can talk to someone at Intel or some other CPU manufacturer and ask, okay, we really want those checks, just give them to us, right? And those checks were provided by Intel, and they are essentially called segmentation. So the whole idea is very, very simple, similar to how we discussed. So let me just illustrate it through an example. It's easier to explain this way. So you say, look, I have two processes, process one, process two. I have an address in this process. I literally want each program to have this address as address 0, and this one as address, let's say x55, and this one as well. But they should land on different physical addresses. What's the simplest hardware trick we want to do? We can do. Imagine you control the hardware. You can do anything with the value in the when it's passed to a move instruction. Do what? Wait. Are you saying like? I think what you're saying is that let's make sure that we add some value to the address. Is that what you're saying? Like an offset? Roughly speaking, I agree with you, but let me check. Let me show you how it works. So imagine there is a special hidden register in the CPU, and when this process issues an address 0, we add the value in this register. This register has the base of the segment, right? So then, like really, the address which hits this physical memory is base plus the original address 0, right? And if you do it here, this base will be different. And despite the fact that address, which we used here, like my move instruction, which loads something in the EBX, like has 0 here, and it has 0 here as well, right? Because the base is different and the base is controlled by the operating system, the physical address will be somewhere in a different range, right? So we just shifted the address space, which means that, okay, cool. If we add the base to every address in a program, and also at the same time do the limit check, similar to the checks which we just did in software, like saying, okay, is your address like above or beyond your highest allowed address, which is called the limit, or like if you say your limit is equivalent to a size, right? Then it's a check in hardware which we want, right? So no matter which address this program issues, it can only access its green range of physical addresses, right? So that's a simple trick, and this is really what CPUs were doing and still doing, right? We say, where does this base address come from? So how will you want to keep it in the CPU? As a CPU designer, what will be your solution?
Register.
In some kind of a register, but since you want to support many processes, right, you will eventually run out of registers, and what you want to do is to have a table in memory of base addresses and switch between them, right? And this table is called a global descriptor table, and literally the table is controlled by the operating system. It sits somewhere in memory, somewhere, for example, here, right? And then every time you switch between process, you can switch to a different table and stuff like that. And essentially you say, look, from this table, we will be getting the base of the segment, and we will call this a segment, and the limit to perform this check in hardware. Correct. So let me just explain it in a second. So for example, just to illustrate the complete figure here, so still my now written is in AT&T assembly. So just the address is inside the EBX register, the load in the EAX. So EBX contains this value, 30010, right? And the value for this process x55, since we shift with the base, we hit, and the base of this process is 110000, you end up with 410010, because this gets added with the base, and this is the physical location in memory which the instruction actually accesses. And the same for the second process, but the base here is 51000, right? And so, the base will be 21000, right? Because you added with 3. And just to make sure that we understand how it works, so those segment registers, essentially CPU has additional segment registers. They can be different on Intel for code, stack segment, data segment, and 3 segments which you can use at will. Essentially, your compiler can generate. And essentially what happens here is that in front of every instruction, you kind of have a choice of choosing a segment. So for example, here, when you do a move instruction, you're saying you are accessing a data segment or your heap, right? An operating system can control where the heap is allocated by essentially setting up a table in memory for this process. And this table contains essentially bases and limits of a segment, and the segment register itself, just an index into that table. So if it's 1, then you go and read the value 1 from this table, right? So instead of like value 0, for example, or value 2. And value 2 might be a stack segment. And so your SS register will contain 2, for example, right? So, and why do we have multiple segments? Back then, again, it was providing some flexibility. So instead of like having a single segment for the entire program, they were saying, okay, maybe you're gonna load different libraries, so some dynamic loading. So you will switch between the segments, switch between like memory locations which you can access. And that was the idea, I guess, back then, right? So the question about the operating system, let me just like quickly explain how it works. So like literally, there is a special register on the CPU, which is called global descriptor table register, which contains the address of the table, which operating system loads when it switches to the process, right? And after that, essentially, you say, look, that's the table which controls which regions of memory you can access with different bases here, right? And after that, the compiler generates code which says, okay, code segment is 1, stack segment is 2, for example, stuff like that, right? And the reason you can, for example, distinguish code and data segments, because you can solve this set on attacks by saying that the code segment is read-only executable, right? So you allow to execute instructions, but you cannot write that segment, right? Which is an additional degree of protection in your program. Okay, so the algorithm in real x86 life goes exactly like we said. So what you're doing is that you say, for example, you're doing a move instruction, your data segment contains value 1, you use it as hardware uses it as an index into this table, global descriptor table, which reads the 2 things from this table, like multiple things, but the 2 important things for us are base and the limit. So you say, whatever address I'm issuing here, like it's 30010, I have a base which is stored in the table. I will do just simply an addition, right, to the address. And this is the physical address which the software accesses, right? So just the same simple idea over and over, just this is the way how it's implemented. Okay, so we got it. And just to make sure that there are multiple ways to construct multiple tables, right? So, and CPU doesn't really tell you which way they want. You can really, when you switch from one process to another, you can simply change the entries in this global descriptor table. Or you can change the value of the global descriptor table and global descriptor table register altogether, switching from one green table to this table, which describes the access rights of the yellow process, right? And I think both approaches were taken in the past. We will see how x86 actually switches, like when we do the context switch and how they maintain the global descriptor table. But roughly, conceptually, each process will have its own global descriptor table. Good question. So I guess let me rephrase what you're asking. You're asking, can the green process, for example, change its own table or not? Like, can it? What do you think? In a way, I drew the diagram.
It looks like it's before the offset of that process.
Right. In my drawing, the table does not overlap with the addresses which the process can access. If the process accesses address 0, it physically can access this address. If it accesses its max address, which is controlled by the limit, which sits here, right? It can access this, this bytes, right? But no matter which address it issues, right? If it issues something past, hoping to do an overflow, for example, right? Overflow, like wrapping around like all 32 bits, trying to issue an address which reaches this address range, it's still past the limit, right? So in my construction here, the process cannot access the global descriptor table. And operating system will have its own global descriptor table, which allow it to access the entire address space, right? So it can like control all the tables of all the processes, right? That's kind of clever trick here. So because we say, look, we just let the processes run. They can choose the entry in the table by changing the code segments, stack segment, data segment registers by saying 1, 2, 3, 4, 5. And if we allow a specific range by configuring it in the table itself, then yes, the process can access those ranges, right? But otherwise, no, right? Do you get it? And this is like, it's a first example of the hardware-based isolation mechanism, right? And you will see another one, page tables, right? But this is like, it's relatively simple. It's just one table, but still seems to be reasonably powerful. Any questions about it? Let's stop. It's kind of important to understand how it works because, as I was saying before, first, you cannot enable page tables without enabling segmentation. So you will anyway have to control them to some degree. And second, I was saying that those segment-based tricks are coming back to our life after so many years of being irrelevant because we want like very fast isolation boundaries within the process itself. So essentially people, like I said, okay, sorry, like two more like one deviation from the main course. So WASM is great. The reason WASM is used because it allows you to isolate untrusted code like Quake within the process and run it, right? On, for example, on the edge. Like I said, on the edge, it's just because it's a use case, but let's just say it's inside the process. But WASM introduces like this 10 to 2x overhead, right? And so it's not ideal. And people are saying, okay, can we bring back the segments? And maybe the segments will allow us to isolate Quake in a more efficient way with an overhead of like 5% maybe. And you need it, right? So in modern life. So that's why the segments are coming back. Okay, there was a question.
Yeah. Can you explain again?
Right. So when you switch between from one process to another, you obviously want to switch the access rights. So the green one can only access this range of addresses, right? And the yellow one should access only this range of addresses, right? There are different ways. Imagine your isolation mechanism is this table, right? Global descriptor table. You have two ways of doing it. Either you have to go ahead and patch every entry in the table, which says, okay, now your base used to be this address, and now it will be this address, right? Right? Because you're changing the access rights. So now suddenly whatever code will be running next will be able to access the yellow region, right? Or alternatively, and it's a decent design choice if you have a small number of entries in the table. If you have a tons of entries, it's easier to switch this register to point from this table to this table, switching all at once, right? And the next instruction will be checked against this new table. Do you think you understand? Yeah. Okay, thank you. I appreciate the question actually, because I believe that many people might be confused. Okay, any other questions?
Can we say that each process has a local descriptor table and OS has
Yeah, so you bring it up yet another table which Intel has, which is called the local descriptor table. And I honestly don't remember the details. I don't want to go into those details. You can do a lot of different tricks with those two tables. I would like to only cover global descriptor table for now. Although like, I would agree with you that if we carefully read the manual, we'll come up with ideas for how to use both. But let's not go into this. Like, it's not worth it in this class. Okay, anything else? So XV6 will be using only the global descriptor table. That's why I'm covering only this one. Okay, good for now? Okay, cool. So we came up with this new mechanism. In the CPU, it introduces something what is called a new addressing mode. And this addressing mode is called logical addresses. Let me tell you what it is. So now, instead of just having a value, like if you have a move instruction, which had this EAX, like actual value of the address, like let's say 55, we also have a second part, right? The actual index into the table, right? Because we have this, suddenly we have a table. It's always enforced, right? So you need to have something in your segment register, which is, let's say, for example, data segment, right? And it has to match whatever you want to find in this table, right? So this part of the address is called effective address. That's an actual address in the register. This is called segment selector, and these two combined are called a logical address, right? So if you read an Intel manual and it says logical address, that's what they mean, right? So again, and the result of this translation when you go through and fetch like a value from the global descriptor table, you add the base address with the effective address with an add operation. The result of it is called linear address. Again, this is terminology. It's really confusing. I agree. When you open an input manual and they say logical address, linear address, well, man, really, you have to come back to this slide and or the slide which will be a little bit later in this lecture, and quickly double check what is logical, what is linear, right? I will not be super specific about them, but still I ask you to at least be able to identify which one is which, right? Okay, so relatively simple. So we have this segment register will contain roughly an index into the table. This entry itself will contain a bunch of different values. We care about, not a bunch, but some values. We care only about the base, which we were covering, the limit, which defines the size, and the access rights, right? The access rights can be executable, read-only, and writable, right? That allows you to separate pieces of the program which you don't want to be overwritten, for example, right? And also, the other reason why we're covering the segment is that the segment, this entry in the GDT, will contain something what is called the privilege level, which will be important later. But roughly speaking, CPU has 4 privilege levels, starting from 0, the most privileged, usually used by the kernel, and ending at 3, the least privileged, which is used by the user programs, right? And we'll be switching between them later, and I will explain how it works. But what's important to remember that these privilege levels are kept in the global descriptor table here. So this value 0 or 3, which we will see later, 0 is used by the kernel and 3 is used by the user program, is actually here in the table. That's why you cannot even use paging without configuring global descriptor table, because you need to know what privilege level you're running at, and that's kept in this global descriptor table. We'll come back to it later, don't worry, but just heads up. Okay, offset is easy, right? So it's just a value in your register, right? And so it gets added with the base. And so your translation is you take effective address which you have in the register, you take the selector which sits here and use it as an index in the array, which is actually a global descriptor table, and you take a specific field which is based out of this entry in this array, and you add the base plus the offset, right? Again, very, very simple. I said it already 10 times. Okay, question?
What's the width of the base address? You said the offset is 32 bits, right?
Right. So the base can be also roughly 32 bits.
That could be overflow.
Yeah, there can be, but the way the base and the limit works, yeah. So you have to be careful. And you have to make sure that you understand what you're doing if you're overflowing the limit, right? Can be overflow, which is unfortunate. Okay, so but the translation works as I was saying. So essentially, we end up with a linear address, and at a high level, we achieve this isolation scheme which we wanted to achieve. Again, those segment registers, they are slightly smaller. They only 16 bits, which limits the size of your global descriptor table. But it's okay. So Intel people decided that it's enough. You don't need many more segments. And typically, segments are associated with one of the 3 types of memory regions, right? Code, data, and stack, right? And roughly speaking, from what I was just trying to explain,
where is heap?
Heap is a region of dynamic memory from which your memory allocator allocates objects, right? malloc, for example, that's a heap. So what I was saying is that it seems that I implied that in front of every access, so for example, if you have x equals to 1, I should insert a segment selector, like ds, for example. If I access something on a stack, I should probably put something like stack segment in front of it. If I have a variable in a data section, again, ds here, right? if I invoke a function, I should probably do something like a code segment, right? And then like invoke a function. But we never seen this before. And we really saw the code which compiler generates, right, in my lectures. So what happened to those segments? How come we never seen them before? Although I implied again that the machine doesn't even run without enabling this global descriptor table. Any guesses for what happened? How come you were never aware? I believe that, okay, how many people heard about the segmentation? I mean, I understand we have a segfault, so we know that this mechanism exists, right? But how many people like ever seen anything like this? Code segment, stack segment. 1, good. 2.5. Okay, good. That's not bad, but okay, this is the real, like, my question is like, how come we write these programs, we never see the segments ever, but it still runs underneath? So what's going on? Any guesses? Well, we saw the code, like which compiler generates for us. So we saw the machine code, no segments around. So how does it work? Correct. So not register, but instruction. So, and that's a nice ergonomic design decision. Intel says, okay, well, guys, instead of writing this code, which is super cumbersome, we can probably just assume that if you access the variable in the stack through a push instruction, you should use the stack segment. If you really want to override it, then yes, in front of a push instruction, the assembly allows you to put an explicit segment value. And similar for in front of a move instruction, we assume a data segment. If you do a jump, then you're using a code segment, right? And in most cases, which we're seeing, it just works because like you don't need any tricks with segments, right? In modern life, the segments are used only to represent something what is called thread local storage. So in languages, it's variables which are private to a thread, right? So I think in C++ you can say something like thread local, right, qualifier, which meaning that if you start a new thread, the value of this variable will be different, right? It's implemented with a segment, so either FS or GS. So essentially the value of GS decides where this, like it's kind of like a data section, but for a thread. So the thread will have its own private thread local data section, and it's addressed relative to the GS or FS segment. So if you disassemble the code with thread local variables, you will see the use of either GS or FS, depending on the operating system, right? But everything else is just one data section, one segment, right? Okay, so this is kind of cute. We kind of understand that, okay, we can do it. So instead of writing, you can always write it. So there is a format which allows you to encode it, but really you just don't need to unless you really want to do some specific trick with a segment. So as I said, everything is just implied, right? Okay, so just to kind of like sum up, okay, so we understood we have the segmentation mechanism. What did we achieve? Now, like we achieved 2 things, right? So we have an illusion of a private address space, meaning, what does it mean? What do I mean by that? I mean that you don't have to relocate the program. You compile it, link it. Let's imagine you say it's linked to run at address 0, and you can load it multiple times. You just have to give it a new segment, right? New data code and stack segments, and it will run. It will, each of the instances of this program, like WC, for example, will have its own address 0. In physical memory, since we're adding the base, they will go to different memory locations, right? So it will have its own private data section, private code section, private stack segment, and stuff like that, right? And that's interesting because you say, well, we can implement fork now, because if I ask you a question, okay, so how do you implement fork? Remember the fork just clones the address space. So what the operating system will do on fork? Right, so it will say, okay, like I create a new data segment, right? And I will just simply copy the content of the old data segment into the new data segment. Same for the code, same for the stack. And the addresses will make sense because you don't have to patch every pointer. The pointer which points into the data section will remain valid, right? That's how you build fork. That's why it works. And all the variables are the same, just because you literally copied them, right? And that's nice. And we achieve this property of isolation. So this one is one, illusion of the address space. And second is isolation, because simply if you set up the segments correctly, it's the global descriptor table, then no matter which address the program issues, it lands in the allowed region and not the region of the other program, right? I agree with that? Okay, cool. And yeah, segments is actually blazingly fast because this base and limit check, if you talk in terms of a pipeline, they can be done while the same instruction is executing. So it's like, roughly speaking, less than a cycle, right? So you do the check quickly, the segment is there, like the CPU preloads these segments upfront and caches them on the die, and then you essentially just like observe almost no slowdown, unless you like really have a very funky pipeline, which doesn't allow you to do that. But like normal CPUs are not designed this way. Question? Yeah. No, of course it's changed, right? So because let me just no, that's a good question. So and I like those details. So for example, like in this slide I have, let me just erase everything. It's maybe not the best slide to explain, but imagine you this green one invokes a fork, right? Fork leads you to the operating system somehow. I didn't explain it yet. Operating system has a segment or a global descriptors table which allows it to access the entire memory. At this point, you say, look, I will create, you have a green table, I will create a yellow table, I will fill the values in such a manner that the data section starts here instead of here, for example, right? I will simply copy everything from here to here, right? Just memcpi. And of course, now this was process one and this one process two, and some data structure in a kernel will hold the address of this new global descriptor table, which you created somewhere in memory, which the operating system can access, but the process cannot access, right? And when you will be switching between them, you will be reloading this hardware register with the new value. If you switch back from yellow to green, you will reload it to point to green, which invalidates all the cached values of the CPU. It will reread the segments, one-time operation, maybe like 2 cycles if it's in L1, maybe a little more than if it's in lower caches, right? Does it answer the question? Okay, cool. Good question. So obviously the answer is like, you can say yes and no. Yes is a little restrictive because it will be wasting space. So typically when you create a process, there will be some kind of metadata which you keep in a kernel, which keeps information about the address space of a process. Depending on how complex it is, it can be different. In our case, it's probably relatively simple because you say, I remember I loaded the process, the data section was this, the text section was this, then I allocated some space for stack, and then there will be heap, and this is what the size of the chunk right now. And you say, well, maybe I will allow a little bit more space for the heap, and hopefully I will never reach that boundary because there might be a different segment after that, right? But that's how you kind of keep track of it. And this is kind of ties to what I'm trying to explain next, the limitation of this scheme, right? But like, are there any questions about the segments and segmentation right now? Good. So what I wanted to switch to, like, we got these two powerful properties: isolation, illusion of a private address space. Suddenly fork works. This fork is notorious because without the segmentation, imagine if we have this trick which I was pushing, this WASM-like trick. Can you build fork with WASM? And for a poll, but I don't have a question for that. It's okay, like, yes. Can we build a fork with WASM? With software fault isolation? Yes, no?
Yes.
Yes? And you say no? Okay, what's your intuition for no? What will be a problem?
I just intuitively, you're going off of that.
Good. You're like my son.
Very high level.
Yeah.
I just feel like there's too much involved. There's too much.
Right. Right. No. Yeah. Correct. So, but try to find a logical chain and find a real problem why it might not work. So maybe No. Let's be a little bit more concrete. Like imagine, like let me choose this slide again. This was fork. Remember, I just simply said I'm gonna copy this into yellow, right? Will this copy go well?
So like, is it sort of like inserted in the binary?
No, like imagine we build an operating system. It's not about WASM. We just use software fault isolation instead of segmentation, just because we're on some microcontroller which doesn't have segmentation whatsoever. Okay, I got what you're saying. So what you're saying is that you need to patch the limits, right? But remember, maybe it was too fast, but I mentioned that the limits you typically hold in registers. You can dedicate a register to hold the limit, right? And then you can just patch the value in that register. Or alternatively, you can have a well-known location, let's say the beginning of the process in which the operating system will put the limits and make this page somehow read-only. You can read from that, but not write. So that doesn't seem to be a problem, but what will be a problem? Like a real conceptual problem which makes fork almost impossible to do without virtualization of memory. Say again? Can you say, maybe I missed what you said. What you're gonna put in a process? Where? Okay. So remember that fork, when you invoke fork, you kind of jump into the operating system kernel. Operating system kernel has a list or an array of all processes in the system, like process 1, process 2, process 3. And imagine you're forking process 3, you kind of you have a metadata in the data structure here, which says start and end, or if it's more complex address space, then like some kind of array of what the addresses are. And you say, look, I'm creating process 4, I will add it to this list in the kernel. And obviously, you will say, well, I need to allocate enough space between start and end. So you will allocate exactly the same amount of space, right? Like you will patch them because there's a new addresses to start and end, right? But you know this, like inside the operating system, because you wrote it, you know it, right? But the problem arises when you just simply try to copy. At this point, it breaks. So what will break?
Those checks inserted.
Wow, they are here. Let's imagine it's a text section. You copy the whole text section, checks will be copied here as well. If the checks check against start and end, and we agree that start and end might be in the EAX register, then you just, instead of copying the value of EAX register, you're gonna patch it slightly to make sure that it's a little like different, right? But that seemed to be doable. But one thing is really, really hard, or almost impossible. What is that thing? What happens to pointers if you blindly copy the address space? Right, so look, imagine this is the stack. Imagine the pointer on a stack points to somewhere in the heap. When you blindly copy this value, well, it will remain pointing here. And that will fail the check.
Relative offset,
right? So hold on. It's like, do you get the point that you cannot just blindly copy the pointers because they will get pointed to the different address space? When we have virtualization of memory, this address, imagine it's like address A, it will work here as well. It will be A here because the hardware will somehow do the offset, right? But the software will not, unless you have some provision for that. And like you say, all the pointers are relative to some other registers, and you patch this register, right? So, but that's really like, this is where you kind of hit the limitation of fork. So if you suddenly have microcontroller like Roomba, and you want to do fork on Roomba, it becomes suddenly challenging if it doesn't have segmentation. It might not, just for the performance, for the power reasons, right? Roomba. Roomba is a vacuum. Oh, sorry, I keep using Roomba. It's this, you know, like this is like robotic vacuum which runs around your house and cleans. Sorry, it's a brand. Sorry, I shouldn't use the brand name.
Couldn't a super beefy like look in the stack that it has and be like, oh, this was 20 volts previous process that you changed it.
Right. So let me again rephrase for everyone because I forgot about this option. What you're suggesting is that can we really figure out all the pointers on a heap and patch them, right? That seems like a doable idea. And it's possible in some languages, like, for example, in a safe language like Java, Rust, whatever where the pointers are well defined, it's doable. You can figure out all the pointers on a heap, right? Because for Java, you need to do that because you do garbage collection anyway, right? For C, it's almost impossible in a general case because C suddenly can typecast just a value into a pointer and say, that's a pointer now, good luck, right? And parts of Java can too, because there is an unsafe level as well, which like interferes with the actual JVM or the runtime. I actually don't know how the split is done in Java. I only know Rust so well. And so yes, in C it's hard. So you might come up with some ideas for how to adjust the pointers, figure them out, but it's hard for unsafe languages like C, C++. You will have Rust has a lot of unsafe as well, and it will have the C, like unsafe Rust is like C, do whatever you want with pointers, and so like there will be no easy solution for, yeah. But that's okay. The reason I'm talking about it is that yes, you might have in real life, if you really like work on some embedded system, you might have to decide whether you want to support fork altogether, just because of this. It's hard to build, right? So you cannot simply copy if you don't have virtualization of memory. Okay, so let me stop here, and next time, let me just show you this slide of the lecture for the next time. The next we're gonna do is we will finish discussing the limitations of segmentation, and we will move on to page tables, because again, that's the mechanism which we use today, which is like a little bit more flexible. Okay, thank you guys.